So you already saw a video for the first part of 5.2, which is de Moivre's theorem. And I'd like to just remind you of a couple theorems that you saw, or definitions, I guess, more than that along the way. The first one was the absolute value. The absolute value looks a lot like what we'd seen in a couple other situations, right? It looks like magnitude for vectors. It looks like a Pythagorean theorem when you're looking at some of our triangles that we have done. And then the polar form of a complex number is going to be important for us as well. So the complex number z equals a plus bi's polar form is z equals r cosine theta plus I sine theta. And then it gives you a couple of formulas here that allows you to change things back and forth. So a is r cosine theta, b is r sine theta. R is the square root of a squared plus b squared, and then the tangent of theta is b over a. So we're going to be leaning back into those definitions as we take a look at these different quantities. And we are on example 5. So on example 5, it asks us to write the complex number in rectangular form. And then it tells us that if there's a necessary place to do so, we're going to round to the nearest tenth. So the first thing I'd like for you to take a look at is that cosine of 210, sine of 210 are values that come from the unit circle, right? 210 is on our unit circle. So put your unit circle hat back on and think about what that looks like. At 210, where are we on the unit circle? Which quadrant? Close. We're in 3. Yeah, we're in 3. So we're down here somewhere in 3. 210 is one of our 30 angles or our 60 angles. Do you know which one it is? Is it the one closest to the x or closest to the y if you're at 210? It's closer to the x, yeah. So it's this one right here. Okay, so just reminding you, because it's been a while since we've actually applied a lot of those kind of ideas. This is our point, and so looking at sine and cosine of that point is where we are. So what is the cosine at that angle? Cosine is the x value. Good. It's negative square root 3 over 2 plus I. And then what about the sine value there? Yeah, negative square or negative 1/2. Now, they're both negative because we're in quadrant 3, right? So keep that in mind. Your signs do matter. And then the last thing we need to do is just distribute our 4 through. So if we distribute our 4 through, it's going to cancel with the 2's in the denominators, right? So I actually have negative 2 square root 3, and then I have minus, and then I'll have 2i. Okay, is that all right? So it feels a lot like the things we were doing, a couple of months ago when we're just evaluating from a unit circle on that one. Okay, so let's take a look at why it is that we would like to look at this other version of complex numbers. So we're going to take a look at products for an example of that, and then we'll look at quotients and how those work. So if we have the product of two complex numbers in polar form, and they give us an example, z1 is r1 cosine theta 1 plus I sine theta 1, and z2 is r2 cosine theta 2 plus I sine theta 2. So if we multiply z1 times z2, what we do is we multiply the real components in front. That's friendly, right? So just you're going to multiply the real numbers, r1 times r2. And you're going to add the angle measures inside of the sines and the cosine components. All right? So it's very clean. It's very straightforward. And we can kind of break it apart by component as we're taking a look at these. So another way of describing it is to say that to multiply complex numbers, we multiply the moduli. That's the part at the beginning. And we add the arguments. That's the part that are the angles. Okay, so we're going to take a look at one of those, and our example looks like this. So we're going to multiply z1 times z2, right? Put a dot between it or don't, doesn't really matter. And we're going to do what? What did it tell us that we need to do to multiply these together, these complex numbers? What's it say over here? We do.
Multiply them first.
Okay, we multiply the pieces at the beginning, right? They call the moduli. So that's my 3 and 10 here, correct? So I'm going to multiply 3 times 10. That's the first thing. And then the second thing I'm going to do is I'm going to have the cosine and the I sine. Like those pieces are going to be what they are. But what do I do with the angles? I add them. So over here, I'm going to have cosine, and then I'm going to have 5 pi over 8 plus pi over 16 plus, and then I'm going to have I sine of the same quantity. So I sine of 5 pi over 8 plus pi over 16. This is a really good example of why this is helpful, because pi over 8s and pi over 16s are not unit circle values that you know, correct? So perhaps as we take a look at this, we will end up with some unit circle values that we do know. We may not, but at the very least, we don't have unit circle values the way they stand right now, correct? So doing this in a different way would not be very helpful. We would get stuck with the information we know, or we would have to approximate something along the way. So this piece right here is 30 at the beginning. And let's take this sort of over to the side and figure out what is 5 pi over 8 plus pi over 16. So how do we add those together? What do we have to do? We need to get common denominators. You could look at the denominators and cross kind of a cross. It's not cross multiplication, but kind of look at the cross like that. There might be a simpler way of doing that to just recognize that one of them is double the other one, which isn't bad either. For example, if I just double my first fractions value on top and bottom, I'll get a common denominator. So I would have 10 pi over 16 plus pi over 16, and what will that reduce to?
11 pi by 16.
Yeah, 11 pi over 16. Now, it's not a value from the unit circle that we know, but it's at least a more compact version than we would have been able to get in the other method. So we're going to be able to rewrite this then as the cosine of 11 pi over 16 plus I sine of 11 pi over 16. It says to leave answers in polar form, so we can leave it like this potentially. I'm fine if you do that, or you might see them multiply the 30 through, which would just put a 30 in the front. So writing it as 30 cosine of 11 pi over 16 plus 30 I sine of 11 pi over 16, just as a version that you're looking for. There's no need that you have to do that. You can certainly leave it right here, but the other one would be perfectly acceptable if you saw that as well, or if you did that as well. Okay, any questions on that? Okay, so that's multiplying. So think with me for a moment. If when we multiply these coefficients, or these complex numbers, together, we multiply the moduli at the beginning and we add the angles, what do you think might happen if we divide? Okay, we might expect to divide the moduli at the beginning. And what do you think we might expect to do with our angles? Subtract, right? So these things usually work sort of in reverse of one another. So that's our expectation. And in fact, it's exactly what happens. We divide the moduli at the beginning and we subtract the angles. Okay? So these go in hand in hand. So dividing complex numbers, again, allows us to combine the parts at the beginning and to combine the angles in this fashion. So we're going to use the same two complex numbers that we had before, right? These are the exact same problem we had before, but we're going to do this in terms of writing it with division instead of with multiplication. Notice that it says that we're going to leave the angle between 0 and 360. That's not telling you have to turn it in degrees. It's just telling you that you're going to be within one unit circle value. So if you ended up getting a negative, you'd have to change that and make it not a negative value. Or if you got a value more than 360, you'd have to do the same thing. Yes, ma'am?
Can you put the lot?
You bet. Jot those in. You got it? Okay. Is everybody else okay? All right. So let's take a look at the division of these complex numbers. So Z1 over Z2. What will I have at the beginning? 3 over 10. Very good. And then what will I have? So cosine 5 pi over 8. Keep going, Lydia.
Minus pi by 16.
Mm-hmm.
Plus I sine 5 pi by 8 minus pi by 16.
Okay. Is that all right? So kind of like on the last one, I'm going to just move over here to this side and do the subtraction of these. You can certainly do it within that same piece if you wanted to, but we have 5 pi over 8 minus pi over 16, and we will find a common denominator just like before. We can multiply by 2. So this actually gives me 10 pi over 16 minus pi over 16, and that's going to give me, 9 pi over 16. And 9 and 16 don't reduce, so we'll have to leave it as is. So it will end up being 3 over 10 cosine of 9 pi over 16 minus I sine of 9 pi over 16. And again, we can certainly leave it just like that. If you really saw the need for or wanted to check and see that it matched something else you're looking at, if you're checking a solution, they might distribute that through. But this is a perfectly acceptable way to leave this.
Would it be a plus or minus?
Plus typo there. Thank you for that, Beck. Appreciate it. This is supposed to say plus. If yours says minus like mine did, please adjust that. Good catch. Okay, is that all right? All right, so the whole title of our section here was de Moivre's theorem, correct? And that's what we're looking at next, is actually where this is all led up to, which is de Moivre's theorem. So de Moivre's theorem says the following. We're going to let z be this complex number in polar form, which is r cosine theta plus I sine theta. And we're going to see what happens when we raise something to a power. Okay, so n's in nth power, we're looking at integers here, right? Positive integers. So 1, 2, 3, 4, 5. 1's not very exciting, so let's start with 2, right? But anything that we've got a positive power for, and it will work like this. Now, all this really is just an application of what we did with the product formula before. Okay, so I'd like to flip over to the product formula to remind you what we did. What this said is that we multiply the components at the beginning, right? And we add the angles. So if I had, say, let's just write one down simple so you can see why this is working for us based on what we've done before. If I had, say, z to the third, just do it small, then what this would have is it would have r cosine of theta plus I sine of theta, and I would be multiplying it times itself 3 times. Okay, is that okay so far? That's what powers of 3 are, right? You multiply something by itself 3 times. Well, at this point, what's on the right looks like product, correct? And we know how to find products. And while we didn't write it down for a product of 3 things, it's just an extension. We would multiply the values together at the beginning. Well, there's r times r times r. And we would add the angles that are in the middle. So this would be cosine of theta plus theta plus theta. Now, I know this is sort of a funny way to write this, but I'm wanting to show you that it actually leads us where we're going. So bear with me for a moment, and we'll clean it up. Okay, so as said, this is awkward, but if we have r times r times r, that's r cubed, right? And if we add theta plus theta plus theta, then that's 3 theta. And what we end up with is the exact same thing that we had up here at the beginning with n being 3, right? So we take whatever the power is to the first part, to the moduli, and then we multiply that power for the angles. Okay, everybody good? So we're going to apply de Moivre's theorem to the next one. So this one actually says, use de Moivre's theorem to find the indicated power, and it is, again, a power of 3. Okay, so just like the one I just did. And then we're going to write the answer in rectangular form. Okay, so rectangular form means that when we're done, it's not going to have sines and cosines and angles in it. Okay, we're going to clean those up. And so since it's telling us that, by the way, it's also probably worth noting that you'll be able to. Right? They wouldn't be telling you to put it in rectangular form if it weren't something you're going to be able to do. In other words, the expectation is you're going to end up getting something that's unit circle, friendly when we get to the end. So let's take a look. This one says we're going to use powers. Well, according to the theorem over here, de Moivre's theorem, it says that I just need to take the power of the coefficient in front, right? So that's 2. So this is 2, and it's a power of 3, so it's 3. And then I'm going to have the cosine and I'm going to have the sine of the angle multiplied by that same power, in this case a 3. So the 3 is going to become a coefficient for my angle. Oops. So this will be 3 times 10 degrees plus I sine of 3 times 10 degrees. Okay, does that make sense? And what angle is it going to give us? 30 degrees, and that's a very friendly angle, right? Like that's one of our best ones because it's even in, in quadrant 1. 2 cubed would be 8. And then let's take a look. So I'm not going to belabor the point to write it out, but this, of course, we already said is 30 degrees, and so is this one over here. So at 30 degrees, what is the cosine of 30 degrees? Good, it's square root 3 over 2. And what is the sine of 30 degrees? It's 1/2. Let me put a dot here. And then what we need to do? So the multiply the I and the 1/2, I mean the next step though. What would we do next? We'll distribute by 8. Yeah, so we'll distribute the 8 through. So if I do the 8 for the first one, the 2 will cancel the denominator. I'm going to get 4 square root 3. The same thing happens with my 8 and my 1/2. I'm going to get a 4, so it's plus 4i. Okay, so we do distribute that through for sure when we get to this point because it wants it in rectangular form, and rectangular form has it all cleaned up and distributed. Okay, makes sense? Now, think about that. You might say, okay, well, that's kind of a cool trick, but it's saving you a lot. If you actually had to multiply this by itself 3 times, this would be ugly because you have a binomial, which would mean you'd have inner and outer terms. Y'all with me? And then you'd do it again because you'd have a third one that you have to multiply it by. It'd be awful. And you'd still end up with cosines and sines of 10 degrees, which you'd have to approximate because we don't have a unit circle value to find those exactly. Or maybe worse yet, you'd be back to looking at maybe something back in chapter 3, which was everybody's favorite, on how to adjust an angle that you don't know to find it exactly, right? Sums and products and things like that. This is a really friendly component of our formula. Now, this maybe doesn't quite look as friendly because it doesn't really look like it's starting out at all like the last problem, right? Let's take a look. Directions are the same. Still use de Moivre's theorem to find the indicated power of the complex number. Okay, well, right now it's not in polar to even be able to use de Moivre's theorem, is it? So the first thing we have to do on this problem is to turn it into polar. And let me just make a comment as well. Could you multiply this out 5 times? You could. It wouldn't be near as bad as multiplying the last one out 3 times. It really wouldn't in its current form, but it would still be ugly, right? You'd have a binomial. So, I mean, like literally what you would have to do if you did this is you'd have to do, whoops, it started with a 1. 1 minus I times 1 minus I times 1 minus I. This is what you'd have to do. And you'd have to distribute out, FOIL out these two, and you'd have to FOIL out these two, and then you'd have to combine them together with distribution, and then you'd still have to be multiplying it times the 1 minus I at the end. This is really ugly, okay? So we're going to take a look at using de Moivre's theorem because this is not what we're wanting to do. This is not the directions, first of all, and it's also really messy. So let's take a look at something that hopefully if you watched the video before, you'll remember how the details work. We need to figure out where is 1 minus I in our quadrants. So you learned how to graph. I didn't go over that already, but if you remember, the real number components are along the x-axis and then the imaginary are along the y-axis. So which quadrant would 1 minus I be in? It's negative. There's a negative in there. Quadrant 4. Going to be in quadrant 4. So the 1 moves me over here by 1. And the negative I means negative 1i, so it will move me down 1 over here. So this is negative 1i, if you will. So I'm right here is where I am. That's where I am in my quadrants. What I need to know is I need to know what angle measure I'm at. So the angle is measured going all the way around, right, like this. What angle is this down here? Can you tell? It is 315. It's one of my 45-degree angles because I've got the 1 and the 1 measured perfectly evenly. This is 315 degrees. So the first thing I'm actually going to have to do is to take a look at what this looks like in polar form. Now, the other thing that I haven't done yet is I haven't figured out how far off this is. I need to know the length of this piece. How do I find the length of that piece? Pythagorean theorem, or you can go back to the formulas where the Pythagorean theorem is showing up. And it tells you that this r value is going to be the square root of each of these components squared. So I have 1 squared plus 1 squared. It's not a very exciting number, but what is this value going to be? Yeah, square root of 2, right? Square root of 2. So first of all, I'm just rewriting. This is square root of 2. And then I've got cosine of 315 plus I sine of 315. And I'm supposed to be taking all of that to the power of 5. Okay, everybody good so far? So at this point, we have not used de Moivre's theorem. All we've done is we've rewritten it from rectangular form into polar form. Now that it's in polar form, I can apply de Moivre's theorem. So what does de Moivre's theorem say that I'm going to do with, let's just talk about the square root of 2. What's the square root of 2 going to become? Square root of 2 to the 5th, which will simplify, but let's save that for another step. So it's just square root of 2 to the 5th. And then what's going to happen to my angles? We're going to multiply them by 5, which means they're going to get really big, right, Shaylin? Yes, they are. I'm going to have cosine of 5 times the 315 plus I sine of the same, 5 times 315. Trying to keep my brackets in my parentheses. There's a lot going on here. Let's go with those being brackets so that we've separated them a little bit better. All right, how about square root of 2 to the 5th? Let's do that part. So if I have square root of 2 to the 5th, what's it going to be? Well, what if you just have 2 to the 5th? What'd you get? What would you get? You're thinking about multiplying 2 and 5. We want to do a power. So what is 2 to the power 5? It's 32. So this is, in essence, the square root of 32. And then 32 can break apart into the 5s, right? So let's just remind you what that is, right? This is where it came from. There's 5 2s. When we're simplifying square roots, we're looking for groups of 2, right? There's 2 groups of 2. So if I bring each of those out, that's a 4 square root of 2. So at the beginning, I have 4 square root of 2. And there's other ways to sort of process through that. You'll get the same answer in any of those methods, but this is 4 square root of 2. What is 315 times 5? This is sort of my scratch work over here. 1,575. That's pretty big, isn't it? It's certainly bigger than my 360. So we're going to have to do something about that in a little bit. So I've got cosine of 1,575 plus I sine of 1,575. Now, 1,575 is certainly not within the 0 to 360. So how do we get it to be within 0 to 360? Do you remember? And this is like the culminating section. We subtract what? 360. And somebody grab a calculator and let's do that. So if we take 1575 and we subtract 360, what do we have? 1215. Still too big, right, Chloe? So what are we going to do? Going to do it again. Subtract 360 again. Where are we now, Lydia? 855. Still too big? Let's do it again. Do you have it, Shaylin? 495. We're getting closer. And we do it one more time. We have 135. Very good. Back. Okay, so we need to change this now. And what we're doing is we're using reference angles to do this, right? We're using the cyclic nature or the repeating pattern of our circle to be able to keep doing this. So I have cosine of 135. Notice it's still a 45-degree angle. I mean, right? Like that shouldn't necessarily surprise us, but it isn't necessarily going to be in the same location that it was before. So previously, when I was at 315, I was in quadrant 4, but at 135, where am I? I'm in quadrant 2. Yeah. So as I've moved around and done this, 5 times in essence, I have now moved back into quadrant 2 up here, right? This is where I am at this point. So I'm at 135 degrees. Okay, so let's do unit circle values because we're supposed to report our answer in rectangular form. So then, what is the cosine of 135 degrees? Lovely, negative square root 2 over 2. And what is the sine value of 135 degrees? Yeah, it's the positive one, so square root 2 over 2. And then we're going to distribute this through, and some things are going to clean up very nicely. Do you notice some square roots cleaning up? And some denominators cleaning up, right? So let's just over here to the side write this down as multiplication because there's more cleanup than we normally see. So I don't want us to lose track of the pieces. So we have 4 square root 2, and in each case, aside from the negative, I'm multiplying by square root of 2 over 2, right? So the 4 and the 2 here can simplify to a 2. And what does square root 2 times square root 2 become? 2. So all of this is going to result in the number 4. Should be 4. Okay, it should be 4. So on the first one, I'm getting negative 4. And on the second one, I'm getting positive 4i. Okay, is that all right? Now, if you really, really, really wanted to check it and wanted to multiply this out here at the beginning, the part I marked out, could you? You could. You'd have to remember that when you do powers of I, right, every time you get an I squared, it becomes -1, and you've got to do that cleanup as you keep going repeatedly along the way, but you would eventually get back to the right value, or the same value we had before. Okay, so this is another component of de Moivre's theorem is next. So this is de Moivre's theorem. Instead of finding powers, like we did before, we're finding roots. So we're going to let, that W is actually the Greek letter omega, so we're going to let omega equal r cosine theta plus I sine theta. It's a complex number. Omega is not 0. And omega has n distinct roots given by this formula. So this looks very familiar at the beginning. Instead of a power of n, I have a root, instead of a power of r, like r to a power, I have the nth root of r, right? That seems reasonable. If I'm taking the nth root, I'll just do that instead, right? Cool. And the part that happens in between is we're actually dividing by n, okay? We multiplied by n before, so that seems reasonable. And so you might be looking at this and saying, but Dr. Hans, what is this part about up here? Well, here's what happens, is that when we divide a value, it gets smaller. Agreed? And when it gets smaller, what happens is that we could have actually divided something that was bigger than 360, right? It's like, let's say that you had 600 degrees and you divided it by 2. Okay, well now it's 300 degrees and it's within 1 unit circle, right? That didn't happen before. It happened sort of in reverse. We multiplied by 5 and we got 1575, right? And what did we have to do? Well, we had to keep repeatedly subtracting off 360, correct? So this is happening in reverse. We're going to repeatedly add 360 or 2 pi, depending on the version we're looking at. We're going to keep repeatedly adding it before we do the division. So we're doing everything we did before in reverse, but the reverse part of it makes it feel a little bit different on the angles because of the order in which we're doing it. Okay, so I have 2 examples of these. Are you ready? So the first one is a little bit more straightforward, and the reason I say that is because we actually see it written in complex number form. Okay, so I've got 27 cosine 306 I sine 306. It wants us to find the complex cube roots. What does cube mean? 3. So I'm doing this kind of a root, right? A cube root like that of this value. Now, the first part, let me just say, whatever it tells you the root is, it's telling you there's going to be that many answers, okay? So if you're looking for a cube root, you're going to have 3 answers. If you're looking for a 4th root, you're going to have 4 answers. Whatever the root is, that's how many answers you're going to have, okay? It's really important. So like on this one in a moment, I'm going to find the complex 6th root. How many answers are going to be? There are going to be 6 answers, okay? That's important to realize so that you don't make the mistake of like doing more work than necessary or stopping short of what you should have done. Okay, that's how many answers we're going to have when we're done. 3 answers. So we're going to find the cube root of each one of these. So let's look for answer number 1 first. And I'm not going to simplify it completely. I'm just going to set up each of the 3, and then we'll go back and clean them up. So number 1, we're going to take on all of them, we're going to take the 27, we're going to take the cube root. So we've got the cube root of 27. Everybody good with that so far? Okay. And on the first one, we're going to take the angle measure that they give us and simply divide it by 3, because this is a cube root. So cosine 306 divided by 3 plus I sine 306 divided by 3. We'll clean it up in a second, but this is number 1. Leave yourself a little bit of space and we'll go back for it. It won't take much to clean it up. The second one is the cube root of 27 still. It's going to have that part on all of them, okay? And then what we're going to do inside is we're going to take the 306, right? And what did it say I'm supposed to do with the 306? We'll look at it in degree form since we're doing degrees. Well, it says I'm supposed to add 360 to it. Okay? So take 306, and I'm going to add 360. And I'm going to actually write it out like this myself. That way, in case you look at it back at it later, maybe you remember where this number comes from. Because it's going to look like a funny number. And then we have I sine, and it's 306 plus 360 divided by 3. Okay, so this is answer number 2. Answer number 3, still going to have a cube root 27 at the beginning. And what's going to happen on this now is that I'm going to have the cosine. And instead of it being 306, 306 plus 360, it's going to be plus 360 twice. So again, I'm going to write times 2 here. I'm going to add 720 to it because it's a multiplication of 360 times 2. And I want to show you, as we're working with it here in just a second, what will happen if you mistakenly add it, like you get carried away and you go to like you do it a 4th time. You'll see very quickly why that won't actually give you what you're looking for. But let's find these before I show you that, okay? So we're cleaning these up. What's the cube root of 27?
3.
It's 3. So at the beginning of each one of these, we're going to start with 3. What's 306 divided by 3? 102. So my first answer, written in polar form, so we'll leave the 3 out in front. If you moved it through, it wouldn't be the end of the world. But it's 3 cosine of 102 plus I sine 102. Now, it told us to leave it in rectangular or in polar form, or if it didn't, write the roots in polar form. So it did. It said in polar form. So that plus the fact that 102 is not on our unit circle kind of go hand in hand. That's typically how the questions show up, is that if it's left in polar form, it's something they wouldn't have asked you to turn into rectangular anyway, kind of a double check step. So this is one of my solutions. Second one still starts out 3. Now, what is 306 plus 360? It's what? 666. We should change this problem. Oh my goodness. We're about to divide it by 3. Let's do that real quick. What is the division of 666 divided by 3? 222. Okay, everybody good? And then the second part will be the same. I sine of 222. So that's answer number 2. Now, again, the third one, there's a 3. And then what's 306 plus 360 times 2? So 360 plus times 360, or 306 plus 360 plus 360. What do we get? 9 something. What was, I don't have this written down. Somebody's going to have to tell me. Do you have it, Shaylin? What is 306 plus 360 times 2? Just the top part. I just want to write it in for good measure. 1,000 something? 1,026. Okay. And then we want to divide that by 3. So what is 1,026 divided by 3? 342. Okay. Now notice every angle that we got in our answers is between 0 and 360, right? That's not by accident. So I want us to try one more thing. I'd like for you to see what happens if you got carried away and you did it a 4th time. If you take 306 plus 360 times 3. What do you get?
1,386.
Okay, a little bit louder for me, Jamie.
1,386.
386. Okay, 1,386. And then I'd like you to take 1,386. Actually, I'll just write it right here and divide it now by 3.
462.
462. And why is that not okay? It's not less than 360, right? So if you get carried away and you forget that you only have 3 answers and you get to a point where your angle measure is too big, again, it's a red flag that should tell you, wait a minute, I went too far. Cool? Okay. Let's take a look at the last one. The last one's the most interesting. Combines a lot of the different pieces we've been working with today. It says 6th roots, which we already said that means we're going to have 6 answers. And the thing that's really interesting is that if you took 64 is just a real number. It's a nice number even, right? Like it's an integer, it's a whole number, it's fantastic. And if I asked you before you came to class today, what is the 6th root of 64? You would give me an answer and there'd be exactly one of them. What's the 6th root of 64 in the real number system? It's 2. Okay, are you with me? If you took the 6th root of 64, you broke 64 down, it would be 2. Okay? But in the complex number system, there's not one answer. There are 6. That's a little different, right? I end up getting more solutions when I'm working in the complex number system than in the real number system. So let's take a look at what that looks like. Well, for starters, 64, if we're thinking about let me draw it this way, our graph for 64, and this being the real components and this being the imaginary, right? Where is 64? Where is it? It's not in a quadrant actually at all. It's on an axis. Which axis? Yeah, the real axis on the positive side, right? It's somewhere, pardon the scale, but it's over here. Correct? So visually, here's what we're going to do. We're taking the entire unit circle, which is 360 degrees, and we're going to divide it into sixths. So what happens when you divide 360 by 6? You get 60. So there's going to be, this is again a visual to motivate what we're doing. I want to show you. We're going to have an answer over here at 60 degrees. We're going to have an answer over here at 120 degrees because that's adding another 60 to it. We're going to have an answer over here, adding another 20 to it at 180 degrees. We're going to have an answer down here at, roughly speaking anyway there, at, do you know where we are? 240. And then, so that's 1, 2, 3, 4. We've got 5. We've got one more. What happens when I add 60 one more time? I get 300. And my angles are kind of getting tight in there, but I've got one at 300. That's what's happening. I'm taking the unit circle and I'm splicing it into however many roots I'm working with. Here I'm working with 6 roots, so there's 6 solutions, but I'm taking the circle and dividing it into 6 pieces of pie, like a pizza. Okay? If I were working with 4, I'd be dividing into 4 units, right? And they would actually be on the quadrants themselves if I were doing this with 4. If I did it with 3, if I did it with 5, it doesn't matter. I'm doing the same thing imagery-wise. Now let's actually see how the process works out with the algebra components that we were doing, right? Not just the visual for it. Do you have a question about my visual first, Beck?
So where's the 6th one?
The first one is the first. Yeah, so this is the first one we will have will be at 0 degrees. So we'd have 0, and then we'd have 60, 120, 180, 240, and 360. 300, excuse me. So there's 6 of them that way. So we include zeros. We don't include 360s. All right? Okay, so let's take a look at how this works out. So the first thing to do is to write out what it is in terms of the polar form for 64. So the polar form, for 64, so our original, how did they label it? I want to make sure I label it the same way. Omega. Our original omega is 64 at the beginning, and then it's cosine of 0 degrees, because we're on the positive x-axis, plus I sine of 0 degrees. This is the angle, or the the value for 64 written in complex number form. It's not very exciting because there's zeros in it, but this is what it would look like. So finding our roots then, so let's find our first root. So they're all going to have sixth roots in it. So it's sixth root of 64, okay, which we recognize as 2, but I'll write it this way just to make sure that if you see something later that's not quite so friendly, you know what we did with it. And then, we have cosine, and we take that first angle measure, which is 0, and we divide it by 6. And I sine of 0 divided by 6. That's the process. I realize 0 divided by 6 is 0, but again, I'm just putting it in really detailed form because it's not always going to start at 0. If this had started at 30 degrees, I want you to look back and realize that's where you need to start. Okay? So again, I'm going to skip some space. We'll come back and simplify this in a moment. Every single one of them is going to have sixth root of 64 at the beginning. And then we're going to take that angle measure, and again, this is going to look silly because our number is 0, but we're going to add 360 to it. Whatever the angle was, we add 360 divided by 6, plus I sine a 0, add 360, divide by 6. Okay, so this is solution number 2. Number 3 is sixth root of 64. What will the angle look like in its sort of messy looking form for this one? Do you know?
That would just be times 2.
Right. All we do is we put times 2 on the 360 at the end. All right, let's do our fourth one. Sixth root of 64, cosine. How will it change? It's just going to be times 3 at the end, right? Okay, I'm going to have to switch slides so that I have some space for my, you know what, actually I think I have space over here. Let's do our fifth one over here. So I've got my sixth root of 64, and then what? Times 4 at the end, right? So 0 plus 360 times 4 over 6 plus I sine 0 plus 360 times 4 over 6. Might have moved over a little bit too far. Here we go. And then let's do our last one, sixth one, because there's 6 answers. Sixth root of 64, and then what I'm going to do? Times 5. Oops. 0 degrees plus 360 times 5 over 6 plus I sine 0 degrees plus 360 times 5 over 6. Also, another red flag as you're thinking, like, how do I make sure I don't, know where to stop or something like that? If you're numbering them like I did, that's great. If you're not, notice if I'm finding sixth roots, the last thing I multiply the 360 by is 1 less. It's 5. If I were finding eighth roots, the last thing I would multiply by would be 7. Okay? Now let's go back and catch these because all of these are angle measures we know from the unit circle. So this sixth root of 64 is going to be a 2 in each case. I'll change colors to try to distinguish my answers apart this time. So all these are 2 at the beginning. That's lovely. We're going to need probably a little bit more space, and I'm probably going to have to space this out so that I can distribute things through, but that's okay. We'll shift it in a second. At 0, what is the cosine of 0? It's 1. And what is the sine of 0? 0. So this is I times 0, or 0i. We'll list it that way. All right. Yes.
If I is multiplied by 0, would the answer be 0?
So it will have a real number component, yes. Sorry, let me get a backdrop on this one so that we can see it better. Let's just do black. Okay, so those are my 2 solutions that I needed to move because I'm out of space. Okay. And let's shift these over. Hang on. That's what happens when you're not thinking about all the details you need. Oops. At the end. I'm sorry. Oh my word. What happened? We'll come back to that screen in a minute. Let's just do that. Let me move this one over here for now. Okay. Oh, because it's over there still. Isn't that fun? I'll rewrite it. All right. Let's actually clean these up as we go, because as you mentioned, Lydia, this is 0 at the end, so these should have 0. Okay. So yes, it gives you 0 at the end, and so this is really just the number 2. The first one's solution is just 2. The second one, when I look at this one, I have, man, I keep not quite catching my degree markers when I shift things. I have 360 divided by 6. What's 360 divided by 6? This is my 60-degree angle. Visually, you can look back there and see that as well. So at 60 degrees, what is the cosine value of 60? That is 1/2. And the sine value is square root 3 over 2. Let's do it this way. I'll write it to the side. So if I distribute that through, that 2 through, I will end up getting 1 plus I square root 3, or you could write square root 3I. Right? What happens when I do 0 plus 360 times 2 divided by 6? What is this angle right here? All that first one was 60. What's this next one? 120. So at 120 degrees, the cosine value is actually, get in the right spot of where I am, negative 1/2. I'll save you the details for the moment to remind you, but this is negative 1/2. And then I have I, and then the sine value is positive. It's square root 3 over 2. Distributing that through ends up giving me negative 1 plus square root 3I, or I square root 3. I'll put it that direction just so you can see that either of those versions is pretty okay. Okay, we have our fourth one, over here. I don't know where my values went, but 0 plus 360 times 3 divided by 6. All right, so what is 0 plus 360 divided by 6? This one's 180. Ooh, so we're actually on the axis. So on the axis, what is the cosine value on the negative y-axis? It's negative 1. And what's the sine value? It's 0. So this is negative 2, all by its little lonesome self. And that makes sense. What is negative 2 times negative 2? What is negative 2 to the 6th? It's 64. So even in the real number system, there should have been 2 solutions that we didn't think about when we were considering that. Our last 2 are over here, despite the fact that they're kind of all messed up. It was times 3 this time, right? 4. Did I already do the 3? Okay, so I'm at times 4. It's really messy. But what is 360 times 4 divided by 6? What angle measure am I at? We're at 240 for this one. Okay, last details. So this is 2, and then I have negative 1/2 minus I square root 3 over 2, and distributing it through, cleaning it up, is negative 1 minus square root 3 over I. And then our last one, what happens when we have 360 times 5 divided by 6? We get 300. And I have my 2 at the beginning, and then I have 1/2 minus I square root 3 over 2, distributed through and so forth, leaves me with 1 minus the square root of 3I. And those are my 6 values. Okay? Tedious? Yes, but the actual complications are only involving multiplication, division, addition, subtraction, and unit circles. So you guys can do this.